All right, we are going to take a look at limiting and excess reactants and calculating the amount of products formed from a reaction and the amount of excess chemical that remains after a reaction. We're going to do this using grams or other units of our chemicals. So we're going to be using our stoichiometry skills to approach this. If you have not looked at how to do this starting with moles yet, you'll want to start with the other video posted and linked for our class. So how do we solve these questions? We are going to be given questions that give us the amount of our chemicals of both reactants. So say we have a reaction with chemical A and chemical B making chemical AB combination. So we want to take whatever amounts of chemicals that we are given in the reaction scenario in the problem. We're going to convert those to moles of that chemical because we want to base everything we do off of the mole ratio. Okay? The mole ratio is your best friend in these situations. Everything needs to relate to that mole ratio. So what we're going to do once we have our numbers in moles, we need to figure out how many moles of each reactant is needed to react with the amounts given. So we kind of have to compare our amounts that we have and our amounts given, or our amounts that we need. So what I do is I look at my chemical reaction written. I write my first reactant amount in moles above my chemical. So for chemical A, I'd write how many moles, say I'm given 2 moles of it. I'm going to write it above that chemical, and then I'm going to determine how many times that reaction happens. If I have 2 moles and its coefficient is say 1, then I'm doing the reaction twice as many times. So we basically are figuring out what we multiply the coefficient of that chemical A by to get the given amount. So I'm multiplying my coefficient by 2 to get my 2 moles that I'm given. We do that with our other chemicals as well. So let's say this is a coefficient of 3 for chemical B. I'd multiply it by 2 as well and see that I need 6 moles of chemical B. Okay, we're going to look then in our given amounts, and we're going to compare this and say, okay, well, I'm given 6 moles of chemical B. How much do I actually, or I need 6 moles of chemical B. How much am I actually given? So if I'm given more than that, then that means chemical A is going to run out. If I don't have enough of chemical B, then chemical B is going to run out first. Okay, so whichever one runs out first is the one we're going to proceed with. So if chemical A is the one that's going to run out first, we're going to go ahead and just keep going with these numbers. We are going to ignore the given amount of chemical B for now. If chemical B is going to run out, or we don't have enough of that, then we're going to do the same thing, but for chemical B. So we'd say, okay, well, my situation only gives me 4 moles of chemical B. Excuse me. So I'd figure out what am I multiplying by to get to 4 moles and multiply chemical A by that amount. And I'd proceed with these numbers. Okay. Again, this is some example. The examples of this are the video. Tyler DeWitt does a wonderful one, and I posted it on for you guys. So check out that if you need more explanation of how that goes. But we did some in class as well. So now we're going to determine the limiting reactant based on which one will run out first. And it's always good to list your limiting reactant and your excess. Sometimes they ask which one it is, which one's limiting and which one's excess, so it's always good to just practice writing those out so that no matter what, you've identified them and it's very clear. Then we're going to calculate the amount of product formed from the reaction in its desired units based on the limiting reactant. Okay, so based on our amount of limiting reactant. Now, if you're not sure about that part, you can always just go all the way back to whichever chemical is your limiting reactant in its given amount in grams or liters or whatever it is. Start with that and then do your stoichiometry to your amount of product that you want. you're going to get the same answer as if you can track it through, our other method here. You can always go back to that and just do the full railroad tracks for it. And we want to figure out how much product we make. And then if asked, sometimes they ask about the amount of excess left over from the reaction, we're going to calculate that. That is always your given amount of that chemical. So in our reaction, say chemical A is in excess. Then we're going to take our given amount of A, we're going to subtract how much we used of chemical A and get how much is left over. Now, we need these units to match. So if we do it in moles, we need moles on both of them. Or we need grams on both of them. Either way, we need to make sure that whatever we're subtracting are in the same unit, same chemical, and then make sure it gets to whatever units the question asks for. So say we subtract and we get moles, but it asks for grams, then we might need to convert this to grams. So let's see how this works. Here's our question. The most important chemical process for the converting of nitrogen from the air into nitrogen-containing compounds is based on the reaction nitrogen and hydrogen forming ammonia. This is called the Haber process, one of the most important reactions we have. So we want to know how many moles of ammonia can be formed from 86 grams of nitrogen and 12.2 grams of hydrogen. And how many grams of excess chemical is unused? How much is left over? So we've got a lot of information to analyze here. The very first thing we need to do is to change these grams of our chemicals into moles so that we can start analyzing them. You cannot analyze it if they're both in grams because we can't follow a mole ratio in grams. So we're going to take, I'm just going to do this, and do it over here. And take my grams of nitrogen, N2, and I'm going to change it from grams of nitrogen to moles of nitrogen. So in 1 mole, there are, I didn't give myself space, 28.02 grams of nitrogen. So we're going to calculate that, 84.06 divided by 28.02, and we get 3 moles of nitrogen. Now this technically would be 4 significant figures, 3.000, so we can keep that in mind in terms of our sig figs for later. We're going to do the same thing for our hydrogen. We are given 12.12 grams of H2. The mass of hydrogen is 2.02 grams per mole. So that is 12.12 divided by 2.02 is 6.000 moles of H2 hydrogen. So we have pretty nice numbers to deal with right now, 3 moles and 2 moles, or 6 moles, excuse me. And so we're going to use that information and compare them with our chemical reaction and its coefficients. So I'm just going to write out my chemical reaction and do some planning here. So I am given 3 moles of nitrogen. So my coefficient is 1. So if I did this reaction, I would be doing it basically 3 times to get or to use up all that chemical, right? I have 3 moles of nitrogen. Every time I do the reaction, I'm using 1 mole of it. So I'm doing the reaction 3 times. I'm going to do the same thing with my hydrogen. Well, if I do the reaction 3 times for nitrogen, I'd have to use 3 times the amount of hydrogen. So that's 9 moles of hydrogen to go with it. Now, let's take a look at what we have. I am given 3 moles of nitrogen. If all of that reacts, I'm going to need, I'm going to need 9 moles of hydrogen. Well, I'm only given 6 moles. So this reaction will not work. Okay? It will not work because I'm going to run out of hydrogen before I can do that. So I'm going to do the same thing and analyze my hydrogen. My nitrogen won't work. So at this point, we already know our limiting and our excess. My limiting reaction is going to be my hydrogen, my excess is going to be my nitrogen. Okay, and we can check on our amounts doing the opposite. We can take our hydrogen. We have 6 moles of hydrogen. If we do this reaction and use up all of our hydrogen, we can do the reaction 2 times. If I do the reaction 2 times, I'm going to need 2 moles of nitrogen. I have plenty. I have 3 moles, so I have extra nitrogen. So we know our hydrogen limiting and our nitrogen is in excess. Once we identify those 2 things, or that information, we can find our answers that we are looking for here. So, in that case, we are going to make twice as much ammonia. 2 times 2 would give us 4 moles of ammonia in H3. Okay, now, our question does ask for moles of ammonia. So I'm going to put 4 moles of NH3 formed. I'm going to box that. That's my final answer to that question. Okay? This is the reaction and following. And again, this was my given amount. This is what I need to go with it. Okay. Now that I've identified and answered the first question, my second question is how many grams of excess chemical is used or is unused in the reaction. So we're going to start with how much I have. So my excess chemical is nitrogen. I am given 3 moles of nitrogen. And I'm going to go ahead and make sure I've got my sig figs on this. So 3.000 moles of nitrogen is how much I'm given. Okay. In my reaction, according to it, I'm going to need or use 2 moles. And it would follow that same mole ratio. I kind of just dropped all the zeros. Used. So if I subtract those, we can see very easily I have 1 mole of nitrogen left. Well, the mass of that would basically be its molar mass, right? 1 mole is 28.02 grams. So I'm going to be left with 28.02 grams of nitrogen left over, or in excess. And that's my second answer. If the question asks something like how many grams or liters or anything like that for our ammonia, we could just simply convert this 4 moles. This would technically be 4.000 if we were needing to answer in sig figs. Okay, so not too terrible. We just have to get our chemicals to moles first and then do some comparisons, figure out which one's limiting and excess, and find out how much each chemical we're going to use and how much we're going to make of our product. Let's try another one. So adipic acid used to produce nylon is made by the reaction between cyclohexane and oxygen. Now, the other thing that's given here, and it was given on our previous reaction, is these values underneath our chemical reaction. Those are our molar masses. So they're giving those every once in a while on the AP exam. They go ahead and give you the molar mass to save some time. And, you know, sometimes they're not testing if you can calculate a molar mass. They're testing something further. So they provide the molar mass so that you have that number, and you're not having to calculate that and maybe mess up your final result based on your molar mass. So it's kind of nice. So we carry out this reaction with 25 grams of cyclohexane, C6H12, and 25 grams of oxygen. So we have equal amounts in grams, but probably not equal moles of each chemical. So we want to figure out how many grams of adipic acid, our product, which is this guy here, we want to find grams of that product, are formed from this reaction. So this reaction has 2 products. We don't have to calculate the mass of both, just the one it asks for. So just like our other question, we are going to take our 25 grams of each chemical, and we're going to go ahead and change them to moles. So again, they give us our molar mass. So for our cyclohexane, 84.18 grams in 1 mole. And I'm going to go ahead and calculate that. So 25 divided by 84.18. You can already see this is not going to be as pretty of a number. We have 0.0 excuse me, 0, oh no, even worse, 0.297 moles of C6H12. Okay, cyclohexane. We have 25 grams of oxygen. We're going to convert 32 grams per mole of oxygen. 25 divided by 32 is going to give us 0.781 moles of oxygen. All right, now that we have the amounts of both chemicals in moles, we can start doing our comparison. So our reaction, C6H12, we don't care right now much about these states of matter. And really the only product we care about is the adipic acid, which is that fun long chemical. If you want to write the water, you can, but we really don't need it. We're going to focus on those chemicals. So we've got our coefficient, that's our mole ratio, and we're going to analyze this and see which chemical is going to run out first. So if I react all of my moles of C6H12, all of the cyclohexane, I have 0.297. So to figure out how many times I can do this reaction, I'm going to take 0.297 and divide it by 2. And I'm doing the reaction 0.149 times, basically. Okay? 0.297 divided by 2 gives me that. You can always test it. 2 times 0.149, and that gives me 0.297. Excuse me. I'm going to do the same thing then with my other chemical. 0.149 is how many times I'm doing the reaction. So 5 times 0.149, and I'm going to get 0.745. 745 moles. So this one's how much I'm given. This is how much I need. I need 0.715. I have 0.781 given. So I have more than enough. So if I use up all of my C6H12, I will have leftover of my oxygen. That means that my limiting is my C6H12. We know that if we use all of it up, I'm going to have excess oxygen. So we can use that information to determine our limiting and excess. We don't need to analyze the other chemical because we can already tell which one's going to be in excess or which one we can have leftovers of. So we can continue from there. If I react all of my C6H12, again, my reaction's happening 0.149 times. And the other thing you can notice is it's a 2-to-2 ratio. We should basically end up with the same moles as our given amount. So we have 0.297 moles. Excuse me. So I'm going to make 0.297 moles of H2C6H8O4. Fun chemical. Now, my question asks how many grams of that I'm making. So we're going to go ahead and change that from moles into grams. Our molar mass is given up above, so 146.16 grams per mole. And we can go ahead and calculate 0.297 times 146.16. We want 3 significant figures on that because our given had 3, so 43.4 grams of adipic acid, H2C6H8O4. And we've answered our first question. All right, now let's tackle the second question. So our second part again says how many grams of excess chemical is unreacted. So we want to figure out how much is left over. So again, I'm going to go back to my list. My excess is O2. So I'm going to say, all right, how much O2 was I given? Well, I've already converted it to moles. So I have 0.781 moles of O2 that I was given. And I'm going to subtract how many moles was used. So according to my reaction up here, I needed 0.7 0.45. That was a 4 moles of O2. So that's written above the O2 in the chemical reaction. That's how much I need, or how much is used if that chemical proceeds, or if that reaction proceeds. I'm going to subtract those, so 0.781 minus 0.745, and we get 0.036. Remember, when we do subtraction or addition, we just line up our decimal places. We want 3 decimal places in our answer because that's what's in all of our numbers. Moles of O2, and that's how much we're going to have left. Now, it does ask for it in grams, so we're going to go ahead, and this is fine. You can just attach on your conversion, moles of O2, and we know that there's 32 grams per mole of O2. Again, that's given up here right underneath that reaction. So we're going to multiply that out. Times 32, we get 1.1. We only have 2 sig figs now, so 1.2 actually grams of O2 left over. And that is our second answer. All right, we're going to take a look at one more example here using some different units. So we have 14.5 liters of hydrogen gas and 6.72 liters of oxygen gas at STP. To form water, we want to find our limiting and excess reactants. We want to know how many grams of water are formed and how many liters of excess we have remaining. So both of these are volumes, and it's at STP, so we can change our liters to moles using our molar volume. So 14.5 divided by 22.4 gives us 0.647 moles of hydrogen, and 0.72 divided by 22.4 gives us 0.300 moles of oxygen. All right, so now we've got moles of each chemical, so we are going to take a look and compare our amounts and see which one's limiting and excess. We're going to base it off our mole ratio of our balanced reaction. So I'm going to start with one of my chemicals. I'm going to start with my first reactant, hydrogen. So I have 0.647 moles of hydrogen. So let's see how many times we can do the reaction. 0.647 divided by its coefficient of 2 gives us 0.324. So that's how many times I'm doing the reaction. So this is how much I'm given. So how much I need of oxygen, 0.324. So I need the coefficient of 1 times 0.324, which is 0.324. Moles of oxygen is how much I need. Now, we compare that to how much we are given of oxygen, and we don't have enough. This reaction will not work that way. So I need to base it off my amount of oxygen. So 0.300 moles of oxygen is how much I'm given. And I know that that is going to be my limiting reactant. So I'm going to go ahead and list that. My limiting is O2, and my excess is hydrogen. That says excess. So if I'm given 3 moles of oxygen, that means I'm doing, 0.3, I'm doing the reaction 0.3 times. So that means that if I multiply that by each reactant, I'm going to need 0.600 moles of hydrogen is how much I need to go with it. Well, I have plenty. I have 0.647, so that's going to be my excess. So now I want to figure out how much water I'm going to make. Well, I'm going to multiply by that same number, 0.3. So, and it would be technically 0.300. So I'm going to get 0.600 moles of water from this reaction. Now, we want to know how many grams that is. So I'm going to go down here and do my conversion. 0.600 moles of water. The molar mass of water is 18.02 grams per mole. So 18.02 times 0.6 gives us 10.8 grams of water are produced from the reaction. All right, our last part is to find our liters of excess chemical that remains. So our excess chemical, let me do this in green, is our hydrogen. We are given 0.647 moles of hydrogen, and we used up or needed 0.6 moles of hydrogen. So we can see from that we have 0.047 moles of hydrogen, of H2, that looks a mess, moles of H2 left over. Now we do need to get that into liters because that's what it asks for, and that's the unit that it started in. So we want to change moles of H2 into liters of H2. It's still a gas at STP, so we would multiply it by 22.4. So 0.047 times 22.4 is going to give us 1.0, we get 266, so 1.1 liters of hydrogen gas left over. So that gives us our excess amount. So we've seen 3 examples here, given different units, grams or liters. The key is that this process here, using our mole ratio, is the same. The only thing that's different is the units we're given and the units we want at the end. So try those ones out that I assigned in class. Thanks.